Good morning, everybody, and welcome to another webinar in the Industrial Heating Equipment Association series on sustainability and decarbonization. I'm Brian Kelly, a recent past president of the IHEA Board of Directors, and on behalf of the association, I want to thank you all for joining us for IHEA's largest sustainability webinar to date. We are excited to continue the series on such an important topic for everyone in the industry. I'd also like to announce that IHEA is launching the 2024 Industrial Heating Decarbonization Summit. This will be held October 28th to 30th in Indianapolis, Indiana. The purpose of the summit is to forge a sustainable path to decarbonization for all companies in our industry. We're finalizing the program now and we'll have registration open very soon, so be on the lookout for that in the email announcements we'll send out. All of the details will be posted on IHEA's website at www.ihea.org. Before we get started, I'd like to remind everybody that all attendees are on mute. If you have any questions along the way, please type them in the questions panel and we will address them at the end of the seminar. One last announcement, this webinar is being recorded and will be available in the sustainability section of IHEA's website within the next few days. You'll receive an email once that link is available. Now I'd like to introduce the presenter for today's webinar titled Making Decisions, Gas versus Electric. Ben Bernard has worked for surface combustion for 16 years and his current position is Vice President of Global Sales. In his sales role, he is actively engaged with the customer's furnace selection and specification process, as well as heat treat process development. He has a Bachelor of Science in Materials Science and Engineering from Michigan Technological University, and Ben is an active member in both the Metal Treating Institute and ASM's Heat Treat Society. So Ben, thank you for joining us and take it away.
Yeah, good morning, everyone. Thank you, Brian. So as Brian said, this webinar is Making Decisions, Gas versus Electric. So a little bit about myself and who I work for quickly. Surface Combustion is a furnace OEM. So we build and design industrial furnaces, as well as make process gas controlled atmosphere generators. And through this, we actually provide the systems in order to enhance the physical properties as a value-added process to improve the materials characteristics and to improve their performance and the competitiveness of our customers' products. Surface has been in business since 1915, so we have a lot of history, so we can combine the tradition and integrity with tomorrow's technology. And we're talking about what's coming up in the future on this webinar here. As a furnace OEM and as others that provide furnaces, Surface Combustion is what we would say energy neutral on the selection of gas or electric heating. We can design either gas heated systems or electrically heated systems, and we offer both. What we intend to do here, like in this webinar, is to educate the customer on how it affects their application and other aspects of their operations. This definition is actually IHEA's definition of electrification that I wanted to share here. It's reducing the emission of greenhouse gases or carbon emissions by converting fossil fuel usage to electric power supply by sustainable sources. That is one of the main topics here on the macro level, and it's the sustainable sources is really the secondary scope from the plant. So with that in mind, the overview of today's webinar is going to talk a little bit about a macro level, what's affecting the decisions of gas versus electric today, talk a little about gas heating systems and electric heating systems that are available, then compare some applications on a specific furnace type with selecting either gas or electric and how that might impact the actual furnace design, and then some conclusions. So overall, an overarching macro level discussion here is we're looking at the commercial markets, some geopolitical issues, and regional demographics. After COVID, there's been a lot of supply chain recovery, And with the supply chain recovery, bringing things back near shore for geopolitical issues as well. But through this, there's environmental accords, global conflicts, and in each one of these topics, you can see at the bottom, energy, 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 and it goes by like prices for the operations and commercial, geopolitical issues, the policy that's being in place and being enforced now, and then regional demographics, where you are located and what kind of energy you have available in your area. So boardrooms more and more have been looking at this environmental sustainability and governance aspect for investors to invest money in their organizations. The ESG is paramount on a lot of decisions coming down for capital equipment. So we've been getting asked more and more to look at electrification of furnace designs. The ramp up of industrial production, relocate nearshoring. As you bring the production back, you're bringing it back with this the purview that you're going to be needing to look at electrification. And then we're back to energy. You have to consider the policy, the availability, and the costs. Excuse me. So in the US, and this goes back to sustainability, this chart is just showing where we are today with energy mix and emissions. Sustainability was to move from greenhouse gas emitting energy, where we are today in the US, to more sustainable energy. And as you can see, there's a mix of power sources that we have, but most of the power in the US here is from coal and natural gas. So if the US was an emission factor of 1, you can see our colleagues in Canada, who have a lot of hydroelectricity, are lower emitters. Mexico is on par with the US right now with their energy mix. And then France and Sweden are much more sustainable in the energy and have lower emission factors. The US greenhouse gas emissions that we're looking at are for industrial processes on the right. And we're looking at future targets to 2030 that are much lower here for each of these industries that are broken out. So overall, there are some opportunities. Looking for some subsidies, grants, or utilities cost sharing. It'd be wise to check into some of these opportunities. Grants are always a challenge to prepare, but they're worth looking into to see if you can have some networking and some co-development of projects. You can check on the federal and local subsidies for bringing production back to the US or into your existing plant. And then utilities are a good resource to see what kind of opportunities there are and to see what kind of available energy there is in their network. Now, as we go to the plant floor from the macro level, we've typically been looking at what the best application is based on the amount of heat you can put into the furnace to try to get you the most production for your operation. But the environmental push for electrification has been pushing the pollutants upstream to the scope 2, and the sustainability efforts, we would rather consider them, consider all the costs that you have from your plant operations, such as capital expenditures, maintenance, and operating costs. But really what we have is this push for electrification, environmental push. So we are still waiting for renewable sources to make a larger impact in the USA. So waiting for government subsidies and renewable energy infrastructure aren't readily available. They're not the quick fix. So we're left to decide between some of the other opportunities here. Obviously try to optimize and get the most out of our equipment most efficiently. You can look at electrification by retrofitting some of the equipment that you have currently. And you can also ask for capital monies in order to invest on new equipment with the electric heating systems as an energy source. So as far as making decisions, the historical thought process was to select the best furnace for a specified process first, then consider gas versus electric heating. And what we're going to be talking about here in this webinar are natural gas heated furnaces and resistant heating, electric heating elements. There are different types of gas heating or burners that you can look into. We're just going to comment on a couple of those. And there are different electric heating methods that could be topics for other discussions, from infrared to induction heating, but we're just going to be talking about resistance heating elements. For gas heating, there are two types. You can have direct fired or indirect heated furnaces. This goes to the delineation is direct fired. Your process gas or process atmosphere inside your furnace are the products of combustion. Some materials can be treated in that way, and typically it's the in-process parts that are in between, an annealing step or some kind of heat treatment step that's in process that will have continued operations in your plant. It can be set up to have recuperation for higher efficiency as well. And the fuel source is typically hydrocarbon. There are some oxy-fuel operations for glass melting, but really for this one, we're talking about natural gas burners. Indirect heating, we have sealed radiant tubes with recuperated excess air burners. This is separating the natural gas products of combustion from the process atmosphere, which you can then select for your furnace. It can be air once again, but it makes more sense to have a protective atmosphere such as exothermic or endothermic gas for the material that you're trying to process, and nitrogen or other inert atmospheres can be used as well. The indirect heating radiant tube is typically used for final component heat treatment. It can also be used for in-process heat treatment. The chart on the right is showing the efficiency of natural gas fired equipment at different temperatures. So if you have a specific temperature or process that you're looking at, like if we're doing carburizing and we're looking at 1700 degrees, you can get a recuperated well-tuned burner somewhere in the 65% efficient range, where if you're generating that power with natural gas at a power plant, that's what the gold line is, you're really having a lot of transmission losses to have an electric heated furnace, where you're going to be at like 45% efficiency. So it does make a lot of sense to have natural gas on a furnace still today. Here's an example of a alloy radiant tube, which has indirect heating. The U-tube is one of the more common types of radiant tubes that are installed in furnaces. The setup is that you have a burner going down one of the legs of the U, and the exhaust is coming out the other leg, where then you would have a recuperator that heats up the air, and preheat air is then put into the burner to increase efficiencies. The advantages of this compared to some of the other burners that we'll see is that there's fewer burners and recuperators required in the setup. So there's a lower installed cost for this type of U-tube, but you have lower thermal efficiency than some of the other alloy radiant tubes that we'll see here. These are some of the varieties of radiant tubes that are the U-tube that I talked about burns down one leg and exhausts out the other. This Trident tube has burners going from the outside legs and has a common exhaust down the center. And similar, the double P type has some exhaust recirculation inside of the burner, inside of the radiant tube. This gas-fired radiant tube is actually a single-ended radiant tube, and it has alloy tubes with an internal recuperator. So the burner would send the flame through the center of the burner tube, and along the walls of the radiant tube, the exhaust would exit the burner. This gives higher thermal efficiency with the residence time of the flame. But there's only one leg or one tube, so you need more burners and recuperators to get the same amount of heat input. And so there's a higher installed cost. If we look at materials selection on the radiant tube, we're changing the alloy radiant tube in this design for a silicon carbide radiant tube, which has a greater heat flux and heat release to the furnace chamber. So it has the ability to reduce the number of burners or radiant tubes that you have inside the furnace. It has the same setup as the single-ended radiant tube, but just with the silicon carbide tube. It would have the highest thermal efficiency and the longest tube life. Now, noting that the longest tube life, you're removing the high temperature thermal creep of the alloy radiant tubes that you have. So it's eliminating that. That's what helps extend the tube life. But the tubes themselves are fragile, and you have to take care not to have any mechanical contact with the tubes. And there are still safety system requirements for mandatory flame supervision that get a little complicated with the silicon carbide tubes. And just the cost of the silicon carbide tubes themselves makes this option the highest installed cost. So we're going to look at some of the electric heating technologies that can be applied. Overall, the advantage of the electric heating would be that in theory, it's 100% efficient. As soon as you turn it on, all the heat is going into the chamber, but we do have some transmission losses from the energy from scope 2. You do remove all the pollutants from the heating system at site. And then you have better working conditions around the furnace as well. You don't have any heat coming off the burners, so it's nicer to work around, not as noisy. You don't have to have the blowers for the combustion system. And it also has the best temperature uniformity and control. Some of the disadvantages today are that payback is limited due to operating costs and the cost of utilities. The capital costs are expensive for VRTs and for electrical control, and maintenance costs are still fairly high for some of the types that we're going to look at. And they are susceptible to breakage and failure, and you're only limited to thermal radiation in a lot of the instances here. So we're looking at electric resistance heating. These are the types of electric resistance heating systems that I've included here. There are plenty of other designs, but the ones that I'm going to show are canned bayonet, which are pretty much radiant tubes. Again, a Pro Electric design, which is a tube rod overbend type. ERT is electrified radiant tube. There's rod overbend, more with smaller diameter rods, and silicon carbide. So the electric heating elements inside of a radiant tube, They would be put inside of a single-ended radiant tube like the gas heated system, so they can be applied in the same type of, let's say, form as the gas-fired radiant tubes. So this might be an option for retrofitting if you had single-ended gas-fired radiant tubes. These have low initial costs and good temperature uniformity, and they actually perform better compared to gas at lower temperatures. One of the advantages here is if you're looking at retrofitting or in a new design, that they can be used with hydrocarbon atmospheres such as endothermic or exothermic gas. And for maintenance purposes or even for manufacturing purposes, you can remove these elements from the outside of the furnace. You don't have to enter the hot zone for confined space. The disadvantage, again, was operating cost and the maintenance cost. Just a note, as you have to change out the radiant tubes every 2 to 3 years, you're more than likely going to have to change out the heating element, because as you try to remove it, you're going to have some ceramic spacers that break, or that you're going to have, the wires that are susceptible to breakage. So it's a good idea to change both the radiant tube and the electric heating element while you're doing the maintenance there, which makes it costlier to maintain. This electric heating elements are also good for hydrocarbon atmospheres, such as RX gas for carburizing, endothermic gas. And as shown in the photo, the element is actually a tube, a bent tube that has an airstream going through the center of it. So it's 330 alloy. So it's good for these atmospheres. The airflow through the center actually helps self-decarburize, pulls the carbon out of the tube, so it extends the life. And it's a very robust system. It's an inch diameter, so it has extremely low risk for breakage. It has good temperature uniformity because you can have a bank of these along your wall. Let's say on a batch interval quench furnace, you can have up to 3 of these on either side, and you can tune them from front to back, so you have very good flexibility to get tight tolerance on temperature. And they also do perform well as a common theme for electric heating at low temperatures. This has the longest life expectancy out of the electric heating options that we'll share here today. The major disadvantage for the Pro Electric is that you have to enter the furnace in order to remove these elements, but after doing some inspection, they could last much longer than what's shown here if you follow the burnout and other maintenance instructions for the furnaces. This rod overbend electric heating element is different from the Pro Electric because it really is rod. It's not a tube. These are anchored to the wall and actually embedded in the ceramic fiber insulation modules. So you can wrap the furnace walls with these heating elements. They have high thermal efficiency and they're fairly easy to install and easy to maintain. You can just remove one and then re-weld it to replace the area. So they make them a good option for a cost-effective solution for electric heating. One thing that you'll have to check on is the application guide and check with the heating element provider, because these elements are not suitable for all atmospheres, and they are made out of different elements, so you have to select the right element for your application. This ERT design, which is an electrified radiant tube, it's like the U tube that we had shown previously, or actually this one is a Trident tube. On the bottom left, you'll see a lot of copper bus bars going around the outside of the radiant tubes on on the exterior of the furnace. This would actually make the three-legged Trident tube the heating element, and you would have resistance heating on the Trident tube. This technology was developed in the 70s to be able to switch between electric and natural gas, as you know, the utilities costs were fluctuating in the 70s, but it could still apply today if you wanted to have both options available, although it does come with a higher price tag and more maintenance because of you're maintaining and installing dual systems here. The silicon carbide resistance heating elements. This one here is a dual leg silicon carbide heating element where it's installed at the top of the furnace of this rotary hearth furnace. And you can see there the light yellow lines are the glow bars that are extending into the furnace around the inner diameter of the furnace that has been removed to show the inside. These silicon carbide elements have high thermal efficiency, and they have maximum operating temperatures that go above indirect gas heating, so you can apply them to higher temperature processes. These elements actually do get brittle and will break if they're stressed at all. The high maintenance cost for these really is that you have them set up in a series of 3. So as you have to change one of them, you should probably change all of them that are on that circuit. Otherwise, you have to adjust you'll have different resistivities that will cause some other maintenance issues. So in hydrocarbon atmospheres as well, you want to make sure that you're not getting any shorting out and making sure that you have good connection or insulating the elements from any kind of carbon buildup. So now moving into an example comparing gas versus electric. The first example is going to be a batch integral quench furnace. This batch integral quench furnace is shown a photo on the right. It has a hot zone with the RX endothermic gas and natural gas enriching in the hot zone. And then it would be, once it exits the hot zone, it comes out to the vestibule that's shown here into the oil quench that's at the bottom of this vestibule. Typically used for carburizing, carbonitriding, and ferritic nitrocarburizing or neutral hardening. The furnace used in the evaluation of the data I'm going to share, it was a 36-48-36 hot zone size, and the load weight was 2,500 pounds, including the fixture and the parts. So that's gross loading. Operating at 1,700 degrees, carburizing for 6 hours, and I mentioned the process atmosphere already, with a net heat release of 512,000 BTUs per hour. Other assumptions in the calculations are a net heat release of 50 BTUs per square inch per hour and 90 BTUs per square inch per hour for alloy, radiant tubes, and silicon carbide materials, respectively. I'm sharing the natural gas costs that we're using in the calculation. These can be rerun for any of your local actual costs at your plant. But it was $10 and then 10 cents per kilowatt hour for comparison. And all the installed costs, when we talk about total costs here, we're including all these miscellaneous items, just making sure that they're all included to make sure you have a full system, such as burners, radiant tubes, heat recovery devices, air blowers if required, exhaust hoods, installation, and all the other components. And we're just looking at 6,000 hour per year operation. So these tables that are comparing the different types of heating sources, at the top you'll see alloy tubes, alloy single-ended, silicon carbide single-ended radiant tubes, and then the final two columns are the electric heating options. So the first three are gas heated. As we go down the columns, you can see how many tubes are required for each of the heat sources, the tube material, and then really what we're trying to do is get in the same amount of heat input for each of these options. And then we'll see what kind of operating cost we have to do the cycle. So with the heating system, operating cost for 2,500 pound load, and you can see that the cost going from the gas heating to the electric is more expensive for the same process. And in the installed system cost, you can see the silicon carbide, as I mentioned in the center, is most costly. And then the total annual operating cost at the 6,000 hours is shown, and the 20-year utility cost is shown at the bottom. You can see that electric heating is most expensive, but their installed cost of the system is less. So if you're looking to invest in electric here now and have the assumption that there will be less expensive renewable energy in the future, that would be something that you can invest in now and look for ways to conserve and to turn to renewable energy. Some of the maintenance costs considerations are the same. It's showing the gas heated on the first three columns and electric on the final two. The Pro Electric has the highest operating reliability for electric, while atmospheric contamination, the single-ended electric heating element, has the highest reliability. So in the alloy U-tubes and alloy are most susceptible to atmospheric contamination. So combining the total lifetime cost, this is comparing both maintenance and operating costs. It tells you the frequency for replacing some of the components like the alloy radiant tube and the silicon carbide radiant tubes, and the alloy radiant tube for the electric heating elements. That it has air blowers for the gas and transformers for electric, and the annual maintenance labor requirement. And over the total lifetime, maintenance costs are shown in the third from bottom row. And then combining the two that we showed earlier, the utility cost and the maintenance cost, the total cost for the entire system over 20 years, you can see the silicon carbide single-ended radiant tube with gas heating has the lowest overall, but trying to go to electric, the Pro Electric would have advantages in this specific furnace application. As far as process control, we mentioned temperature uniformity, and the gas heating options here are probably limited to plus or minus 10 degrees Fahrenheit, depending on the furnace application, specifically for this batch integral quench furnace. And then you can get down to plus or minus 5 degrees using electric heating options. The impact of a 10-degree temperature spread can lead to it can impact the process to have a variation of 5% case depth in a carburizing cycle for deep case cycles. So the temperature is important. So going to electric, if you have deep case cycles, could be one of the options or decision points. So there are some other standards here for AMS 2750. Most of them, the batch integral quench furnaces, this would meet those standards. And then it mentions low temperature process of FNC could be better at electric heating. Excuse me. For environmental considerations, this slide actually considers scope 2 input from electric heating, electric power generation, assuming that most of the power is coal generated. So it gets penalized for that here in this presentation. So it's showing that burning natural gas at your furnace actually has lower CO2 production than electric. As you go to renewable, this will definitely change. We're going to compare a couple other furnace types here, comparing gas versus electric. For a couple type of continuous furnaces, a direct fired versus an air electric furnace, and then vacuum furnace to show some options there. So the pusher is a continuous type furnace where the gas heating in this type of furnace compared to electric, you would be paying 7% more on a maintenance cost. It takes a little bit more time to maintain and keep the burners going with the quantity of burners on a continuous furnace. However, when you use electric bayonet heating in place of gas, the operating costs are like 78% more costly. So the operating costs, again, are a main concern when trying to choose gas versus electric. This is a table showing in blue the gas-fired versus electric options for a single row pusher using process endothermic gas, RX gas. Process gas has its own carbon footprint, but it is required in order to do the value add process for heat treatment. So that will be carried for either option here, gas or electric. In the carburizing furnace, it says 3100 connected, but really it's 2000 for the heating. In the electric heated, you can see there's 1100 CFH of natural gas required, and the notes down below say that is for intermittent flame screens and for purges, and then the column for enriching process gas is always required. So this just gives a sum total and gives a comparison that we can calculate and offer both types, even for continuous pushers. This type of furnace is a belt furnace. It could be a mesh belt, or in this case, a cast belt furnace. Cast belts offer heavier loading. The gas type here was a direct fired with pulse fire and recuperation. It cost 5% more, not much of a penalty or savings going either way here. And the connected heat input for the process and production volume was 3.5 million BTUs connected. The electric option here employed a mix of both the modular rod overbend type heating elements you can see above the hearth, and below the hearth we actually used bayonet inside of radiant tubes to help with the mechanical damage below of anything falling down from scale or the like. And it had a connected power of 1 megawatt. So you have to make sure that you have enough facilities, power from your utility company when you're going to be looking at installing this. It adds up quickly. Here's an example of direct fired versus electric air furnaces. These would probably be very common in heat treat and in process heat treatment. The direct fired uses product of combustion. It helps mitigate the amount of scale growth on steel parts. You can get radiation and convection with burner placement and flue exhaust, so you can get a good recirculation inside the furnace. The electric air furnaces tend to have, would create more scale at higher and higher temperatures with the presence of oxygen. But you could, at this point, put in optional nitrogen gas or have it in a retort in order to keep the work in the process free of oxygen, although then that enters into its own scope 2 energy requirements for industrial gases. I wanted to include something on vacuum furnaces because typically for vacuum furnaces, the choice is electric. And that seems to be the most common choice here, but there are opportunities for gas, and some of the reasons why you would choose one or the other. Gas actually can have this radiant tube that has a tight seal and a vacuum tight seal, so you can actually set burners inside of the vacuum chamber using silicon carbide or alloy radiant tubes. Silicon carbide is shown in the furnace at the bottom. The temperature ranges using gas heating in a vacuum furnace are ideal for vacuum carburizing and also for tempering. So if you're in an area with gas, it is a good opportunity here to use gas in that instance. For electric, it's best for high temperature and deep vacuum applications, really all vacuum applications, but ideally for high temperature and deep vacuum. There are different types of materials of construction you can use, whether it be graphite heating elements as shown in the photo at the bottom, or it can have an all refractory metal hot zone with resistance heating as well, electric. And then you'll need the VRT investment and maintenance. This gives an example of a vacuum temper cycle using the utility costs shown at the top, gas and electric, comparing them for a 1,200 pound load at 1,050 degrees. The operating cycle, it's cost per cycle, so it's operating costs for the cycle shown on the time temperature chart, and it's half the price to do it with gas. So this would be an opportunity here that's seldom thought of for vacuum, but if you're electrifying, then you know that you can calculate how much it's going to cost to do the same cycle. So for some, excuse me one second. For retrofit options, some of the considerations you should think of for electrification, if you're going to retrofit your current furnaces with electric resistance heating elements, you have to consider the plant infrastructure. Do you have the switch gear? Do you have the power supply? Is it available from utility? Are you in a region where electric costs less than typical for, and maybe there's some advantages there. There are major mechanical modifications that are required to the furnace, and these are often underestimated because you have to touch the furnace twice. You have to uninstall, you have to modify the casing perhaps, and then install the new heating system. And this is always on the operations floor. It's probably the most inefficient place to do this, as opposed to trying to get a new furnace with a new heating system installed. But when you look at retrofitting, you're probably, and normally you're going to need to derate the furnace capacity and throughput production. You're not going to be able to fit as much heating in as you could with the natural gas. You just get much more heating input with the natural gas. And then you want to make certain that you're studying the element selection in the material type, for example, for the application. And again, it could be an application for a batch electrical quench furnace, continuous belt, or a vacuum furnace here. They all have different atmospheres. And you want to make sure that you are talking to your furnace supplier or the electric element provider to do that. So as you're looking at the different types of heating elements that you might want to retrofit your furnace with, this gives an example of the Pro-Electric electrified radiant tube, canned bayonet, single-ended radiant tube type, or the silicon carbide. It gives some of pros and cons of each and different applications. So if you were going to use it in an endothermic atmosphere, it gives you the best options here for maintenance element removal, maintenance type for breakage, and what you have to do for maintenance here. And then expected element life. And if in the radiant tube, you have to replace as well with the electric heating element, as I mentioned before. So as we consider all this and we look at making decisions for gas, the current situation is that we'd ask that I'd ask that you don't make your greenhouse gas problems worse. If your electric utility is using coal or fossil fuels to generate the energy, it makes sense to use natural gas at your plant to do the heat treatment. It's higher efficiency, and as you can see in the table below, this is considering electric power generated from a natural gas fired utility, and it has a couple different furnace types. There's the scope 2 in the electric footprint row. So if you have gas fired, you actually are only generating 53 kilograms CO2 as opposed to the scope 2 addition to get double that for the electric heating options. So if you're going to choose electric, it would be a no-brainer if we could actually say that your utility is using high renewable, or if you have access to renewable energy, because the scope 2 emissions and penalties here that we were considering go away, and the electric on site really helps and removes the carbon dioxide from the operations. And you can see the cold wall electric with a 2-chamber vacuum is very low then at that point here, only using some nitrogen industrial gas, and that's what the scope 2 would be in that case. In conclusion, just to recap, you should first try to select the furnace type based on production, material, and try to see what kind of process you're going to need for atmosphere, temperature, any kind of contaminants that would be coming from the part or from the process, and how that would apply and affect your heat source. So in this paradigm here, you would be looking at the heat source third to make sure that you have the right heat treatment in the process. Although currently the headwinds are to make the heat source choice first for electric, and then you want to look at the cost for investment, operating and maintenance costs here. But going into these costs are the cost for the environment and trying to help with giving environmental benefits for the workplace and Earth. So going electric in the future would be great for everyone. Just giving an update of where we are today and how we would consider choosing between gas and electric. So the final thought was just operating costs have a significantly higher impact on the lifetime costs. And I think at this point, that's what I had to present, and see if anybody had any questions.
All right, and thank you very much. Very educational for me. I've often wondered and discussed that with a lot of our customers on what are the variables that go into decision of gas versus electric and beyond maybe regional and things of that nature. But a couple questions. One, are there opportunities for, say, hybrid designs with both gas and electric heating?
Yeah, there are. You can, if you wanted to retrofit and try to limit the amount of gas you're putting in, we could take a look at putting electric heating into the single-ended, where the single-ended gas-fired radiant tubes were before. We could put the bayonet style in there. That would be on a continuous furnace. You'd probably want to do that in the last zones that are the holding temperature, so you don't have to have as much heat input in those zones. So you can have electric in those areas, but where you need the highest gas or the highest heat input, you might make sense to have gas in those areas. So like at the entrance of a continuous furnace, it would make sense.
Okay. Another one here. What are the temperature ranges that are most typical for most common, I'm sorry, for gas heating?
For gas heating, I would say you can go as low, typical of like 350 degrees to around 2150 would be typical. You could stretch them on the higher end a little bit more, maybe another 100 degrees, but that would be the range that you'd be looking at. And then the sweet spot would be in the middle there, about 1400 to like 1900 degrees.
And same, I guess the same question. What are the typical temperature ranges, or most, I should say, most common for, say, electric resistance heating?
Um, for electric, you can go lower. Mentioned a couple times the lower uniformity at the lower end is better. So you can drop it down to 300 easily. 250 could be potentially a good application there too. And then the range is much higher at the maximum. It can go above 2400 degrees. Some applications can go into like the 3000 degrees, depending on what you're trying to do. And in some resistance heating inside of vacuums, it can get up to that temperature.
Cool, very interesting. I just had something to add when you had done some of your calculations for gas and electric cost, but also on the CO2 consequences and the scope 2 emissions. Just for everybody's knowledge, you can contact your utility and they will actually give you a CO2 footprint or pounds per kilowatt. So that could be your comparison. If you have your fuel usage and all that, you can actually make a comparison. And most utilities are pretty open on their plans to decarbonize, right? So this is all a journey, and kind of leads me up to um, really thanking everybody for attending the webinar. Remember to visit the IHEA website at IHEA.org. Click the sustainability tab on the menu bar for more information on sustainability and decarbonization and our upcoming webinars. And as on the screen, we hope to see you at IHEA's Decarbonization Summit in October. Watch for a link for a survey. Take a few minutes to share your feedback for that. That makes it's valuable for us going forward to make sure that we're giving you guys what you want. And Ben, again, thank you very much for your time and your expertise. And everybody have a great day.
No, thank you. It was fun. I appreciate it.